Learning objectives. In this chapter, the user will learn the following in detail. Types of data and cluster analysis, partition-based clustering, hierarchical clustering, density-based clustering, grid-based clustering, model-based clustering, discussion on scalability of clustering algorithm, outlier analysis, parallel approach to clustering. Introduction. Cluster analysis. Cluster analysis, or simply clustering, is the process of partitioning a set of data objects or observations into subsets. Each subset is a cluster, such that objects in a cluster are similar to one another, yet dissimilar to objects in other clusters. The set of clusters resulting from a cluster analysis can be referred to as clustering. In this context, different clustering methods may generate different clusterings on the same data set. The partitioning is not performed by humans, but by the clustering algorithm. Hence, clustering is useful in that it can lead to the discovery of previously unknown groups within the data. Cluster analysis has been widely used in many applications such as business intelligence, image pattern recognition, web search, biology, and security. In business intelligence, clustering can be used to organize a large number of customers into groups where customers within a group share strong similar characteristics. As a data mining function, cluster analysis can be used as a standalone tool to gain insight into the distribution of data, to observe the characteristics of each cluster, and to focus on a particular set of clusters for further analysis. Alternatively, it may serve as a pre-processing step for other algorithms, such as characterization, attribute subset selection, and classification, which would then operate on the detected clusters and the selected attributes or features. Clustering is also called data segmentation in some applications because clustering partitions large datasets into groups according to their similarity. Clustering can also be used for outlier detection, where outliers, values that are far away from any cluster, may be more interesting than common cases. Density-based clustering. To find clusters of arbitrary shape, we can model clusters as dense regions in the data space, separated by sparse regions. This is the main strategy behind density-based clustering methods, which can discover a cluster of non-spherical shape. DB-scan. Density-based clustering based on connected regions with high density. The density of an object can be measured by the number of objects close to it. DB-scan, density-based spatial clustering of applications with noise, finds core objects, that is, objects that have dense neighborhoods. It connects core objects and their neighborhoods to form dense regions as clusters. A user-specified parameter greater than 0 is used to specify the radius of a neighborhood we consider for every object. The neighborhood of an object O is a space within a radius centered at O. Due to the fixed neighborhood size, the density of a neighborhood can be measured simply by the number of objects in the neighborhood. To determine whether a neighborhood is dense or not, DB-scan uses another user-specified parameter, min points, which specifies the density threshold of dense regions. An object is a core object if the neighborhood of the object contains at least min points objects. Core objects are pillars of dense regions. Given a set D of objects, we can identify all core objects with respect to the given parameters and min points. The clustering task is then reduced to using core objects and their neighborhoods to form dense regions, where the dense regions are clusters. For a core object Q and an object P, P is directly density reachable from Q if P is within the neighborhood of Q. Object P is directly density reachable from another object Q if and only if Q is a core object and P is in the neighborhood of Q. Using the directly density reachable relation, a core object can bring all the objects from its neighborhood into a dense region. In DB-scan, P is density reachable from Q with respect to and min points in D. If there is a chain of objects P1 to Pn such that P1 is equal to Q, Pn is equal to P, and pi plus 1 is directly density reachable from pi with respect to and min points for I falling between 1 and n, pi belongs to D. Note that density reachability is not an equivalence relation because it is not symmetric. If both O1 and O2 are core objects and O1 is density reachable from O2, then O2 is density reachable from O1. However, if O2 is a core object but O1 is not, then O1 may be density reachable from O2, but not vice versa. To connect core objects as well as their neighbors in a dense region, DBSCAN uses the notion of density connectedness. Two objects P1, P2 belonging to D are density connected with respect to min points if there is an object Q belonging to D such that both P1 and P2 are density reachable from Q with respect to min points. Unlike density reachability, density connectedness is an equivalence relation. It is easy to show that for objects O1, O2 and O3, if O1 and O2 are density connected and O2 and O3 are density connected, then so are O1 and O3. We can use the closure of density connectedness to find connected dense regions as clusters. Each closed set is a density-based cluster. A subset C, subset of D, is a cluster if for any two objects O1, O2 belonging to C, O1 and O2 are density connected, and there does not exist an object O belonging to C and another object O dash belonging to D minus C, such that O and O dash are density connected. How does DBSCAN find clusters? Initially, all objects in a given dataset D are marked as unvisited. DBSCAN randomly selects an unvisited object P, marks P as visited, and checks whether the neighborhood of P contains at least min points objects. If not, P is marked as a noise point. Otherwise, a new cluster C is created for P, and all the objects in the neighborhood of P are added to a candidate set N. DBSCAN iteratively adds to C those objects in N that do not belong to any cluster. In this process, for an object P dash in N that carries the label unvisited, DBSCAN marks it as visited and checks its neighborhood. If the neighborhood of P dash has at least min point objects, these objects in the neighborhood of P dash are added to N. DBSCAN continues adding objects to C until C can no longer be expanded, that is, N is empty. At this time, cluster C is completed and thus its output. To find the next cluster, DBSCAN randomly selects an unvisited object from the remaining ones. The clustering process continues until all objects are visited. If a spatial index is used, the computational complexity of DBSCAN is big O into n log of n, where n is the number of database objects. Otherwise, the complexity is big O n squared. With appropriate settings of the user-defined parameters and min points, the algorithm is effective in finding arbitrary shaped clusters. Algorithm DBSCAN, a density-based clustering algorithm. Input D, a dataset containing n objects. E, the radius parameter, and min points, the neighborhood density threshold. Output, a set of density-based clusters. Method is as shown on screen. Optics, ordering points to identify the clustering structure. To overcome the difficulty in using one set of global parameters in clustering analysis, a cluster analysis method called optics was proposed. Optics does not explicitly produce a dataset clustering. Instead, it outputs a cluster ordering. This is a linear list of all objects under analysis and represents a density-based clustering structure of the data. Objects in a denser cluster are listed closer to each other in the cluster ordering. This ordering is equivalent to density-based clustering, obtained from a wide range of parameter setting. Thus, optics does not require the user to provide a specific density threshold. The cluster ordering can be used to extract basic clustering information derive the intrinsic clustering structure as well as provide a visualization of the clustering. To construct the different clusterings simultaneously, the objects are processed in a specific order. This order selects an object that is density reachable with respect to the lowest value so that clusters with higher density will be finished first. Based on this idea, optics needs two important pieces of information per object. The core distance of an object P is the smallest value such that the neighborhood of P has at least min points objects. That is the minimum distance threshold that makes P a core object. If P is not a core object, with respect to min points, the core distance of P is undefined. The reachability distance to object P from Q is the minimum radius value that makes P density reachable from Q. According to the definition of density reachability, Q has to be a core object and P must be in the neighborhood of Q. Therefore, the reachability distance from Q to P is max core distance Q, distance P, Q. If Q is not a core object with respect to min points, the reachability distance to P from Q is undefined. An object P may be directly reachable from multiple core objects. Therefore, P may have multiple reachability distances with respect to different core objects. The smallest reachability distance of P is of particular interest because it gives the shortest path for which P is not connected to a dense cluster. Optics computes an ordering of all objects in a given database, and for each object in the database, stores the core distance and suitability reachability distance, and a suitable reachability distance. Optics maintains a list order seeds to generate the output ordering. Objects in order seeds are sorted by the reachability distance from their respective closest core objects, that is, by the smallest reachability distance of each object. Optics begins with an arbitrary object from the input database as a current object P. It retrieves the neighborhood of P, determines the core distance, and sets the reachability distance to undefined. The current object P is then written to output. If P is not a core object, optics simply moves on to the next object in the order seeds list. If P is a core object, then for each object Q in the neighborhood of P, optics updates its reachability distance from P and inserts Q into order seeds if Q has not yet been processed. The iteration continues until the input is fully consumed and order seeds is empty. A dataset's cluster ordering can be represented graphically, which helps to visualize and understand the clustering structure in a dataset. The structure of the optics algorithm is very similar to that of DWScan. Consequently, the two algorithms have the same time complexity. DENCLU, clustering based on density distribution functions. Density estimation is a core issue in density-based clustering methods. DENCLU, density-based clustering, is a clustering method based on a set of density distribution functions. In probability and statistics, density estimation is the estimation of an unobservable underlying probability density function based on a set of observed data. In the context of density-based clustering, the unobservable underlying probability density function is the true distribution of the population of all possible objects to be analyzed. The observed data set is regarded as a random sample from that population. In DWScan and optics, density is calculated by counting the number of objects in a neighborhood defined by a radius parameter. Such density estimates can be highly sensitive to the radius value used. To overcome this problem, kernel density estimation can be used, which is a non-parametric density estimation approach from statistics. The general idea behind kernel density estimation is simple. We treat an observed object as an indicator of high probability density in the surrounding region. The probability density at a point depends on the distances from this point to the observed objects. Figure shows the subtlety in density estimation in DWScan and optics. Increasing the neighborhood radius slightly from 1 to 2 results in much higher density. DENCLU has several advantages. It can be regarded as a generalization of several well-known clustering methods such as single linkage approaches and dbScan. Moreover, DENCLU is invariant against noise. The kernel density estimation can effectively reduce the influence of noise by uniformly distributing noise into the input data. Discussion on scalability of clustering algorithm. Many clustering algorithms work well on small data sets containing fewer than several hundred data objects. However, a large database may contain millions or even billions of objects, particularly in web search scenarios. Clustering on only a sample of a given large dataset may lead to biased results. Therefore, highly scalable clustering algorithms are needed. Partitioning methods. Effective for small to medium-sized datasets. Hierarchical methods. Cannot correct erroneous merges or splits. May incorporate other techniques like microclustering or consider object linkages. Density-based methods. Can find arbitrarily shaped clusters. May filter out outliers. Grid-based methods. Use a multi-resolution grid data structure. Fast processing time, typically independent of the number of data objects, yet dependent on grid size. Grid-based clustering. A grid-based clustering method takes a space-driven approach by partitioning the embedding space into cells independent of the distribution of the input objects. The grid-based clustering approach uses a multi-resolution grid data structure. It quantizes the object space into a finite number of cells that form a grid structure on which all the operations for clustering are performed. The main advantage of the approach is a fast processing time, which is typically independent of the number of data objects, yet dependent on only the number of cells in each dimension in the quantized space. STING, Statistical Information Grid. STING is a grid-based multi-resolution clustering technique in which the embedding spatial area of the input objects is divided into rectangular cells. The space can be divided in a hierarchical and recursive way. Several levels of such rectangular cells correspond to different levels of resolution and form a hierarchical structure. Each cell at a high level is partitioned to form a number of cells at the next lower level. Statistical information regarding the attributes in each grid cell, such as the mean, maximum, and minimum values, is pre-computed and stored as statistical parameters. These statistical parameters are useful for query processing and for other data analysis tasks. The statistical parameters of higher-level cells can easily be computed from the parameters of the lower-level cells. These parameters include the following: the attribute-independent parameter, count, and attribute-dependent parameters, mean, standard deviation, minimum, maximum, and the type of distribution that the attribute value in the cell follows, such as normal, uniform, exponential, or none, if the distribution pattern is unknown. The attribute is a selected measure for analysis, such as price for house objects. When the data are loaded into the database, the parameters count, mean, standard deviation, min and max, the bottom-level cells, are calculated directly from the data. The value of distribution may either be assigned by the user if the distribution type is known beforehand, or obtained by hypothesis tests such as the chi-square test. The type of distribution of a higher-level cell can be computed based on the majority of distribution types of its corresponding lower-level cells in conjunction with the threshold filtering process. If the distributions of the lower-level cells disagree with each other and fail the threshold test, the distribution type of the high-level cell is set to none. The statistical parameters can be used in a top-down, grid-based manner as follows. First, a layer within the hierarchical structure is determined from which the query answering process is to start. This layer typically contains a small number of cells. For each cell in the current layer, we compute the confidence interval or estimated probability range reflecting the cell's relevancy to the given query. the irrelevant cells are removed from further consideration. Processing of the next lower level examines only the remaining relevant cells. This process is repeated until the bottom layer is reached. At this time, if the query specification is met, the regions of relevant cells that satisfy the query are returned. Otherwise, the data that fall into the relevant cells are retrieved and further processed until they meet the query's requirements. An interesting property of Sting is that it approaches the clustering result of DBSCAN if the granularity approaches O toward very low level data. That is, toward very low level data. In other words, using the count and cell size information, dense clusters can be identified approximately using Sting. Therefore, Sting can also be regarded as a density-based clustering method. Advantages of Sting over other clustering methods. 1. The grid-based computation is query-independent because the statistical information stored in each cell represents the summary information of the data in the grid cell, independent of the query. The grid structure facilitates parallel processing and incremental updating. And 3. The method's efficiency is a major advantage. Sting goes through the database once to compute the statistical parameters of the cell, and hence the time complexity of generating clusters is big O(n), where n is the total number of objects. After generating the hierarchical structure, the query processing time is big O (g), where g is the total number of grid cells at the lowest level, which is usually much smaller than n. Because Sting uses a multi-resolution approach to cluster analysis, the quality of Sting clustering depends on the granularity of the lowest level of the grid structure. If the granularity is very fine, the cost of processing will increase substantially. However, if the bottom level of the grid structure is too coarse, it may reduce the quality of cluster analysis. Sting does not consider the spatial relationship between the children and their neighboring cells for construction of a parent cell. As a result, the shapes of the resulting clusters are isothetic, that is, all the cluster boundaries are either horizontal or vertical, and no diagonal boundary is detected. This may lower the quality and accuracy of the clusters despite the fast processing time of the technique. Clique, an a priori-like substance clustering method. Clique, clustering in Quest, is a simple grid-based method for finding density-based clusters in subspaces. Clique partitions each dimension into non-overlapping intervals, thereby partitioning the entire embedding space of the data objects into cells. It uses a density threshold to identify dense cells and sparse ones. A cell is dense if the number of objects mapped to it exceeds the density threshold. The main strategy behind Clique for identifying a candidate search space uses the monotonicity of dense cells with respect to dimensionality. This is based on the a priori property used in frequent pattern and association rule mining. In the context of clusters in subspaces, the monotonicity says the following. A k-dimensional cell, C, k greater than 1, can have at least L points only if every k-1 dimensional projection of C, which is a cell in a k-1 dimensional subspace, has at least L points. Clique performs clustering in 2 steps. First step. Clique partitions the d-dimensional data space into non-overlapping rectangular units, identifying the dense units among these. Clique finds dense cells in all of the subspaces. To do so, Clique partitions every dimension into intervals and identifies intervals containing at least L points, where L is a density threshold. Clique then iteratively joins 2 k-dimensional dense cells, C1 and C2, in subspaces di1 going up to dik and djk going up to djk respectively, if di1 is equal to di1 going up to dik-1 equals djk-1, and C1 and C2 share the same intervals in those dimensions. The join operation generates a new k+1 dimensional candidate cell C in space DI1 going up to DIK-1, DIK, DJK. Click checks whether the number of points in C passes the density threshold. The iteration terminates when no candidates can be generated or no candidate cells are dense. Second step. Click uses the dense cells in each subspace to assemble clusters which can be of arbitrary shape. The idea is to apply the minimum description length MDL principle to use the maximal regions to cover connected dense cells where a maximal region is hyperrectangle, where every cell falling into this region is dense and the region cannot be extended further in any dimension in the subspace. Finding the best description of a cluster in general is NP-hard. Thus, Click adopts a simple greedy approach. It starts with an arbitrary dense cell, finds a maximal region covering that cell, and then works on the remaining dense cells that have not yet been covered. The greedy method terminates when all dense cells are covered. Figure shows dense units found with respect to age for the dimensions salary and vacation are intersected to provide a candidate search space for dense units of higher dimensionality. Effectiveness of Click. Click automatically finds subspaces of the highest dimensionality such that high-density clusters exist in those subspaces. It is insensitive to the order of input objects and does not presume any canonical data distribution. It scales linearly with the size of the input and has good scalability as the number of dimensions in the data is increased. However, obtaining a meaningful clustering is dependent on proper tuning of the grid size, which is a stable structure here, and the density threshold. This can be difficult in practice because the grid size and density threshold are used across all combinations of dimensions in the dataset. Thus, the accuracy of the clustering results may be degraded at the expense of the method's simplicity. For a given dense region, all projections of the region onto lower dimensionality subspaces will also be dense. This can result in a large overlap among the reported dense regions. Furthermore, it is difficult to find clusters of rather different densities within different dimensional subspaces. Hierarchical clustering. A hierarchical clustering method works by grouping data objects into a hierarchy or tree of clusters. Representing data objects in the form of a hierarchy is useful for data summarization and visualization. The hierarchical partitioning can be continued recursively until a desired granularity is reached. Agglomerative versus divisive hierarchical clustering, which organize objects into a hierarchy using a bottom-up or a top-down strategy, respectively. Agglomerative methods start with individual objects as clusters, which are iteratively merged to form large clusters. Conversely, divisive methods initially let all the given objects form one cluster, which they iteratively split into smaller clusters. Hierarchical clustering methods can encounter difficulties regarding the selection of merge or split points. Such a decision is critical because once a group of objects is merged or split, the process at the next step will operate on the newly generated clusters. It will neither undo what was done previously nor perform object swapping between clusters. Thus, merge or split decisions, if not well chosen, may lead to low quality of clusters. Moreover, the methods do not scale well because each decision of merge or split needs to examine and evaluate many objects or clusters. A promising direction for improving the cluster quality of hierarchical methods is to integrate hierarchical clustering with other clustering techniques, resulting in multiple phase or multi-phase clustering. There are several orthogonal ways to categorize hierarchical clustering methods. For instance, they may be categorized into algorithmic methods, probabilistic methods, and Bayesian methods. Agglomerative, divisive, and multi-phase methods are algorithmic, meaning they consider data as objects as deterministic and compute clusters according to the deterministic distances between objects. Probabilistic methods use probabilistic models to capture clusters and measure the quality of clusters by the fitness of models. Agglomerative versus divisive hierarchical clustering. A hierarchical clustering method can be either agglomerative or divisive, depending on whether the hierarchical decomposition is formed in a bottom-up merging or top-down splitting fashion. An agglomerative hierarchical clustering method uses a bottom-up strategy. It typically starts by letting each object form its own cluster and iteratively merges clusters into larger and larger clusters until all the objects are in a single cluster or certain termination conditions are satisfied. The single cluster becomes the hierarchy's root. For the merging step, it finds the two clusters that are closest to each other according to some similarity measure and combines the two to form one cluster. Because two clusters are merged per iteration, where each cluster contains at least one object, an agglomerative method requires at most n iterations. A divisive hierarchical clustering method employs a top-down strategy. It starts by placing all objects in one cluster, which is the hierarchy's root. It then divides the root cluster into several smaller subclusters and recursively partitions those clusters into smaller ones. The partitioning process continues until each cluster at the lowest level is coherent enough, either containing only one object or the objects within a cluster are sufficiently similar to each other. In either agglomerative or divisive hierarchical clustering, a user can specify the desired number of clusters as a termination condition. Agnes, agglomerative nesting, an agglomerative hierarchical clustering method, and Diana, divisive analysis, a divisive hierarchical clustering method on a dataset of 5 objects A, B, C, D, and E. Initially, Agnes, the agglomerative method, places each object into a cluster of its own. The clusters are then merged step by step according to some criterion. For example, clusters C1 and C2 may be merged if an object in C1 and an object in C2 form the minimum Euclidean distance between any two objects from different clusters. This is a single linkage approach in that each cluster is represented by all the objects in the cluster, and the similarity between two clusters is measured by the similarity of the closest pair of data points belonging to different clusters. The cluster merging process repeats until all objects are eventually merged to form one cluster. Diana, the divisive method, proceeds in the contrasting way. All the objects are used to form one initial cluster. The cluster is split according to some principle, such as the maximum Euclidean distance between the closest neighboring objects in the cluster. The cluster splitting process repeats until eventually each new cluster contains only a single object. A tree structure called a dendrogram is commonly used to represent the process of hierarchical clustering. It shows how objects are grouped together in an agglomerative method or partitioned in a divisive method step by step. A challenge with divisive methods is how to partition a large cluster into several smaller ones. A divisive method typically uses heuristics in partitioning, which can lead to inaccurate results. For the sake of efficiency, divisive methods typically do not backtrack on partitioning decisions that have been made. Once a cluster is partitioned, any alternative partitioning of this cluster will not be considered again. Due to the challenges in divisive methods, there are many more agglomerative methods than divisive methods. Distance measures in algorithmic methods. Whether using an agglomerative method or a divisive method, a core need is to measure the distance between two clusters, where each cluster is generally a set of objects. 4 widely used measures for distance between clusters are as follows, where mod of p minus p dash is the distance between two objects or points, p and p dash. Mi is a mean for cluster Ci, and Ni is the number of objects in Ci. They are also known as linkage measures. The equations for the minimum, maximum, mean and the average distances are as shown on the screen. Minimum distance. When an algorithm uses the minimum distance, dmin of Ci, Cj, to measure the distance between clusters, it is sometimes called a nearest neighbor clustering algorithm. If the clustering process is terminated When the distance between the nearest clusters exceeds a user-defined threshold, it is called a single linkage algorithm. If we view the data points as nodes of a graph, with edges forming a path between the nodes in a cluster, then the merging of two clusters, Ci and Cj, corresponds to adding an edge between the nearest pair of nodes, Ci and Cj. Because edges linking clusters always go between distinct clusters, the resulting graph will generate a tree. Thus, an agglomerative hierarchical clustering algorithm that uses the minimum distance measure is also called minimal spanning tree algorithm, where a spanning tree of a graph is a tree that connects all vertices, and a minimal spanning tree is the one with the least sum of edge weights. Maximum distance. When an algorithm uses the maximum distance, Dmax, of Ci, Cj, to measure the distance between clusters, it is sometimes called farthest neighbor clustering algorithm. If the clustering process is terminated when the maximum distance between nearest clusters exceeds a user-defined threshold, it is called a complete linkage algorithm. By viewing data points as nodes of a graph with edges linking nodes, we can think of each cluster as a complete subgraph, that is, with edges connecting all the nodes in the clusters. The distance between two clusters is determined by the most distant nodes in the two clusters. Farthest neighbor algorithms tend to minimize the increase in diameter of the clusters at each iteration. If the true clusters are rather compact and approximately equal in size, the method will produce high-quality clusters. Otherwise, the clusters produced can be meaningless. Mean or average. The use of mean or average distance is a compromise between the minimum and maximum distances and overcomes the outlier sensitivity problem. Whereas the mean distance is the simplest to compute, the average distance is advantageous in that it can handle categoric as well as numeric data. The computation of the mean vector for categoric data can be difficult or impossible to define. Single versus complete linkages. Let us apply hierarchical clustering to the dataset of Figure A, given below. Figure B shows the dendrogram using single linkage. Figure C shows the case of using complete linkage, where the edges between clusters A, B, J, H and C, D, G, F, E are omitted for ease of presentation. This example shows that by using single linkages, we can find hierarchical clusters defined by local proximity, whereas complete linkage tends to find clusters opting for global closeness. There are variations of the four essential linkage measures just discussed. For example, we can measure the distance between two clusters by the distance between the centroids, that is, the central objects of the clusters. Birch, multi-phase hierarchical clustering using clustering feature trees. Balanced iterative reducing and clustering using hierarchies, Birch, is designed for clustering a large amount of numeric data by integrating hierarchical clustering at the initial microclustering stage and other clustering methods such as iterative partitioning at the later macroclustering stage. It overcomes the two difficulties in agglomerative clustering methods: scalability and the inability to undo what was done in the previous step. Birch uses the notions of clustering feature to summarize a cluster and clustering feature tree, CF tree, to represent a cluster hierarchy. These structures help the clustering method achieve speed and scalability in large or even streaming databases and also make it effective for incremental and dynamic clustering of incoming objects. Consider a cluster of n d-dimensional data, objects or points. The clustering feature CF of the cluster is a 3D vector summarizing information about clusters of objects. It is defined as CF equals n, ls, ss within angular brackets, where ls is the linear sum of the n points and ss is the square sum of the data points. A clustering feature is essentially a summary of the statistics for the given cluster. Using a clustering feature, we can easily derive many useful statistics of a cluster. For example, the cluster's centroid x0, radius r and diameter d can be represented as shown on the screen. Here, R is the average distance from member objects to the centroid, and D is the average pairwise distance within a cluster. Both R and D reflect the tightness of the cluster around the centroid. Summarizing a cluster using the clustering feature can avoid storing the detailed information about individual objects or points. Instead, we only need a constant size of space to store the clustering feature. This is the key to merge efficiency in space. Clustering features are additive, that is, for two disjoint clusters C1 and C2 with the clustering feature CF1 equals N1, LS1, SS1 and CF2 equals N2, LS2 and SS2 respectively. The clustering feature for the cluster that formed by merging C1 and C2 is simply CF1 plus CF2 equals N1 plus S2, LS1 plus LS2, SS1 plus SS2. A CF tree is a height balance tree that stores the clustering features for hierarchical clustering. By definition, a non-leaf node in a tree has descendants or children. The non-leaf nodes store sums of the CFs of their children and thus summarize clustering information about their children. A CF tree has two parameters, branching factor B and threshold T. The branching factor specifies the maximum number of children per non-leaf node. The threshold parameter specifies the maximum diameter of subclusters stored at the leaf nodes of the tree. These two parameters implicitly control the resulting tree size. Birch applies a multi-phase clustering technique. A single scan of the data set yields a basic, good clustering, and one or more additional scans can optionally be used to further improve the quality. The primary phases are: Phase 1. Birch scans the database to build an initial in-memory CF tree, which can be viewed as a multi-level compression of the data that tries to preserve the data's inherent clustering structure. Phase 2. Birch applies a selected clustering algorithm to cluster the leaf nodes of the CF tree, which removes sparse clusters as outliers and groups dense clusters into larger ones. For Phase 1, the CF tree is built dynamically as objects are inserted. Thus, the method is incremental. An object is inserted into the closest leaf entry, subcluster. If the diameter of the subcluster stored in the leaf node after insertion is larger than the threshold value, then the leaf node and possibly other nodes are split. After the insertion of the new object, information about the object is passed toward the root of the tree. The size of the CF tree can be changed by modifying the threshold. If the size of the memory that is needed for storing CF tree is larger than the size of the main memory, then a larger threshold value can be specified and the CF tree is rebuilt. The rebuild process is performed by building a new tree from the leaf nodes of the old tree. Thus, the process of rebuilding the tree is done without the necessity of rereading all the objects or points. This is similar to the insertion and node split in the construction of B+ trees. Therefore, for building the tree, data has to be read just once. Some heuristics and methods have been introduced to deal with the outliers and improve the quality of CF trees by additional scans of the data. Once a CF tree is built, any clustering algorithm, such as a typical partitioning algorithm, can be used with the CF tree in Phase 2. Chameleon, multi-phase hierarchical clustering using dynamic modeling. Chameleon is a hierarchical clustering algorithm that uses dynamic modeling to determine the similarity between pairs of clusters. In Chameleon, cluster similarity is assessed based on how well connected objects are within a cluster and the proximity of clusters. That is, two clusters are merged if their interconnectivity is high and they are close together. Thus, Chameleon does not depend on a static, user-supplied model and can automatically adapt to the internal characteristics of the clusters being merged. The merge process facilitates the discovery of natural and homogeneous clusters and applies to all data types as long as a similarity function can be specified. Chameleon uses a k-nearest neighbor graph approach to construct a sparse graph, where each vertex of the graph represents a data object and there exists an edge between two vertices or objects. if one object is among the k most similar objects to the other. The edges are weighted to reflect the similarity between objects. Chameleon uses a graph partitioning algorithm to partition the k nearest neighbor graph into a large number of relatively small subclusters such that it minimizes the edge cut. That is, a cluster C is partitioned into subclusters Ci and Cj so as to minimize the weight of the edges that would be cut should C be bisected into Ci and Cj. It assesses the absolute interconnectivity between clusters Ci and Cj. Chameleon then uses an agglomerative hierarchical clustering algorithm that iteratively merges subclusters based on their similarity. To determine the pairs of most similar subclusters, it takes into account both the interconnectivity and the closeness of the clusters. Specifically, Chameleon determines the similarity between each pair of clusters, Ci and Cj, according to their relative interconnectivity, Ri, Ci, Cj, and their relative closeness, Rc, Ci, Cj. The relative interconnectivity, Ri of Ci and Cj, between two clusters Ci and Cj is defined as the absolute interconnectivity between Ci and Cj, normalized with respect to the internal interconnectivity of the two clusters Ci and Cj. That is, the relative interconnectivity can be shown as represented on screen, where EC, Ci, Cj is the edge cut as previously defined for a cluster containing both Ci and Cj. Similarly, ECCi or ECCj is the minimum sum of the cut edges that partition Ci or Cj into two roughly equal parts. The relative closeness, Rc of Ci and Cj, between a pair of clusters Ci and Cj is the absolute closeness between Ci and Cj normalized with respect to the internal closeness of the two clusters Ci and Cj. It is defined as shown on the screen, where SEC, Ci, Cj is the average weight of the edges that connect vertices in Ci to vertices in Cj, and SEC, Ci or SEC, Cj is the average weight of the edges that belong to the min-cut bisector of cluster Ci or Cj. Chameleon has been shown to have greater power at discovering arbitrarily shaped clusters of high quality than several well-known algorithms such as BERT and density-based DB-scan. However, the processing cost for high-dimensional data may require big O n squared time for n objects in the worst case. Probabilistic hierarchical clustering. Algorithmic hierarchical clustering methods using linkage measures tend to be easy to understand and are often efficient in clustering. Algorithmic hierarchical clustering methods can suffer from several drawbacks. First, choosing a good distance measure for hierarchical clustering is often far from trivial. Second, to apply an algorithmic method, the data objects cannot have any missing attribute values. In the case of data that are partially observed, that is, some attribute values of some objects are missing, it is not easy to apply an algorithmic hierarchical clustering method because the distance computation cannot be conducted. Third, most of the algorithmic hierarchical clustering methods are heuristic and at each step locally search for good merging or splitting decision. The data generative models adopt common distribution functions such as Gaussian distribution or Bernoulli's distribution, which are governed by parameters. The task of learning a generative model is then reduced to finding the parameter values for which the model best fits the observed data set. Algorithm: a probabilistic hierarchical clustering algorithm. Input: D equals O1 to On, a dataset containing n objects. Output: a hierarchy of clusters. Method is as shown on the screen. Model-based clustering. The theme of clustering that allows an object to belong to more than one cluster. Clustering methods under model-based clustering: fuzzy clusters, probabilistic model-based clusters, expectation maximization algorithm. Fuzzy clusters. Given a set of objects X equals X1 going up to Xn, a fuzzy set S is a subset of X that allows each object in X to have a membership degree between 0 and 1. Formally, a fuzzy set S can be modeled as a function fx. X implies 0, 1. We can apply the fuzzy set idea on clusters. That is, given a set of objects, a cluster is a fuzzy set of objects. Such a cluster is called a fuzzy cluster. Consequently, a clustering contains multiple fuzzy clusters. Formally, given a set of objects O1 going up to On, a fuzzy clustering of k fuzzy clusters, C1 going up to Ck, can be represented using a partition matrix M equals Wij into I lying between 1 and n, j lying between 1 and k, where Wij is a membership degree of Oi in fuzzy cluster Cj. The partition matrix should satisfy the following three requirements. For each object Oi and cluster Cj, Wij lies between 0 and 1. This requirement enforces that a fuzzy cluster is a fuzzy set. For each object Oi, summation of j equals 1 to k, Wij equals 1. This requirement ensures that every object participates in the clustering equivalently. For each cluster Cj, summation of I equal to 1 to n, Wij lying between n. This requirement ensures that for every cluster, there is at least one object for which the membership value is non-zero. Fuzzy clustering is also called soft clustering because it allows an object to belong to more than one cluster. It is easy to see that the traditional, rigid clustering, which enforces each object to belong to only one cluster exclusively, is a special case of fuzzy clustering. Probabilistic model-based clusters. In probabilistic model-based clusters, we conduct cluster analysis on a dataset because we assume that the objects in the dataset, in fact, belong to different inherent categories. Clustering tendency analysis can be used to examine whether a dataset contains objects that may lead to meaningful clusters. Here, the inherent categories hidden in the data are latent, which means they cannot be directly observed. Instead, we have to infer them using the data observed. A dataset that is a subject of cluster analysis can be regarded as a sample of the possible instances of the hidden categories, but without any category labels. The clusters derived from cluster analysis are inferred using the dataset and are designed to approach the hidden categories. Statistically, we can assume that a hidden category is a distribution over the data space which can be mathematically represented using a probability density function or distribution function. We call such a hidden category a probabilistic cluster. For a probabilistic cluster C, its probability density function f and a point O in the data space f of O is the relative likelihood that an instance of C appears at O. Suppose we want to find k probabilistic clusters, C1 going up to Ck, through cluster analysis. For a data set D of n objects, we can regard D as a finite sample of the possible instances of the clusters. Conceptually, we can assume that D is formed as follows. Each cluster of Cj, with j lying between 1 and k, is associated with the probability omega j, that some instance is sampled from the cluster. It is often assumed that omega 1 to omega k are given as part of the problem setting and that omega j equals 1, which ensure that all objects are generated by the k clusters. Here, parameter omega j captures background knowledge about the relative population of cluster Cj. We then run the following two steps to generate an object in D. The steps are executed in times in total to generate n object, O1 going up to On, in D. Choose a cluster Cj according to probabilities omega 1 to omega k. Choose an instance of Cj according to its probability density function Fj. The data generation process here is the basic assumption in mixture models. Formally, a mixture model assumes that a set of observed objects is a mixture of instances from multiple probabilistic clusters. Conceptually, each observed object is generated independently by two steps. First, choosing a probabilistic cluster according to the probabilities of the clusters, and then choosing a sample according to the probability density function of the chosen cluster. Given dataset D and K, the number of clusters required, the task of probabilistic model-based cluster analysis is to infer a set of K probabilistic clusters that is most likely to generate D using this data generation process. An important question remaining is how we can measure the likelihood that a set of K probabilistic clusters and their probabilities will generate an observed dataset. Consider a set C of K probabilistic clusters, C1 going up to Ck, with probability density functions, F1 going up to Fk respectively, and their probabilities omega 1 through omega k. For an object O, the probability that O is generated by cluster Cj, with j lying between 1 and k, is given by conditional probability of O given Cj equals omega j Fjo. Therefore, the probability that O is generated by the set of C clusters is conditional probability of O given C equals summation j1 to k Wj Fj of O. Since the objects are assumed to have been generated independently, for a dataset D equals O1 going on up to On of n objects, we have conditional probability of D given C equals product of I equals 1 to n conditional probability of OI given C equals product of I equals 1 to n summation j equals 1 to k Wj Fj OI. Now it is clear that the task of probabilistic model-based cluster analysis on a dataset D is to find a set C of K probabilistic clusters such that conditional probability of D given C is maximized. Maximizing conditional probability of D given C is often intractable because in general the probability density function of a cluster can take an arbitrarily complicated form. To make probabilistic model-based clusters computationally feasible, we often compromise by assuming that the probability density functions are parameterized distributions. Formally, let O1 to On be the n observed objects and 2L to 2K be the parameters of the K distributions, denoted by big O equals O1 to On and 2 equals 2L through to 2K respectively. Then for any object OI belonging to big O with I lying between 1 and n, conditional probability of OI given theta equals summation of j equals 1 to k omega j conditional probability of OI given theta j, where Pj OI given 2j is a probability that OI is generated from the jth distribution using parameter 2j. Consequently, conditional probability of big O given theta equals product of I equals 1 to n summation j equals 1 to k omega j conditional probability of OI given theta j. Using the parameterized probability distribution models, the task of probabilistic model-based cluster analysis is to infer a set of parameters, 2, that maximizes expectation maximization algorithm. The K-means algorithm iterates until the clustering cannot be improved. Each iteration consists of 2 steps. The expectation step, E step, given the current cluster centers, each object is assigned to the cluster with a center that is closest to the object. Here, an object is expected to belong to the closest cluster. The maximization step, M step, given the cluster assignment for each cluster, the algorithm adjusts the center so that the sum of the distances from the objects assigned to the cluster and the new center is minimized. That is, the similarity of objects assigned to a cluster is maximized. An expectation maximization EM algorithm is a framework that approaches maximum likelihood or maximum a posteriori estimates of parameters in statistical models. In the context of fuzzy or probabilistic model-based clustering, an EM algorithm starts with its initial set of parameters and iterates until the clustering cannot be improved, that is, until the clustering converges or the change is sufficiently small, less than a preset threshold. Each iteration also consists of two steps. The expectation step assigns objects to clusters according to the current fuzzy clustering on parameters of probabilistic clusters. The maximization step finds the new clustering or parameters that maximize the SSE in fuzzy clustering or the expected likelihood in probabilistic model-based clustering. Outlier analysis. An outlier is a data object that deviates significantly from the rest of the objects, as if it were generated by a different mechanism. Outliers are different from noisy data. Noise is not interesting in data analysis, including outlier detection. Outliers are interesting because they are suspected of not being generated by the same mechanisms as the rest of the data. Therefore, in outlier detection, it is important to justify why the outliers detected are generated by some other mechanisms. This is often achieved by making various assumptions on the rest of the data and showing that the outliers detected violate those assumptions significantly. Outlier detection is also related to novelty detection in evolving datasets. Types of outliers. In general, outliers can be classified into three categories, namely global outliers, contextual or conditional outliers, and collective outliers. Let's examine each of these categories. Global outliers. In a given dataset, a data object is a global outlier if it deviates significantly from the rest of the dataset. Global outliers are sometimes called point anomalies and are the simplest type of outliers. Most outlier detection methods are aimed at finding global outliers. To detect global outliers, a critical issue is to find an appropriate measurement of deviation with respect to the application in question. Various measurements are proposed, and based on these, outlier detection methods are partitioned into different categories. Global outlier detection is important in many applications. Contextual outliers. In a given dataset, a data object is contextual outlier if it deviates significantly with respect to a specific context of the object. Contextual outliers are also known as conditional outliers because they are conditional on the selected context. Therefore, in contextual outlier detection, the context has to be specified as part of the problem definition. Generally, in contextual outlier detection, the attributes of the data objects in question are divided into two groups. Contextual attributes. The contextual attributes of a data object define the object's context. In the temperature example, the contextual attributes may be date and location. Behavioral attributes. These define the object's characteristics and are used to evaluate whether the object is an outlier in the context to which it belongs. In the temperature example, the behavioral attributes may be the temperature, humidity, and pressure. Collective outliers. Given a dataset, a subset of data objects forms a collective outlier if the object as a whole deviates significantly from the entire dataset. Importantly, the individual data objects may not be outliers. Collective outlier detection has many important applications. Unlike global or contextual outlier detection, in collective outlier detection, we have to consider not only the behavior of individual objects, but also that of groups of objects. Therefore, to detect collective outliers, we need background knowledge of the relationship among data objects, such as distance or similarity measurements between objects. Challenges of outlier detection. Outlier detection is useful in many applications, yet faces many challenges, such as the following. Modeling normal objects and outliers effectively. Outlier detection quality highly depends on the modeling of normal, non-outlier objects and outliers. Often, building a comprehensive model for data normality is very challenging, if not impossible. This is partly because it is hard to enumerate all possible normal behaviors in an application. The border between data normality and abnormality, outliers, is often not clear-cut. Instead, there can be a wide range of gray area. Consequently, while some outlier detection methods assigned to each object in the input data set a label of either normal or outlier, other methods assign to each object a score measuring the outlierness of the object. Application-specific outlier detection. Technically, choosing the similarity distance measure and the relationship model to describe data objects is critical in outlier detection. Unfortunately, such choices are often application-dependent. Different applications may have very different requirements. Outlier detection's high dependency on the application type makes it impossible to develop a universally applicable outlier detection method. Instead, individual outlier detection methods that are dedicated to specific applications must be developed. Handling noise in outlier detection. Noise often unavoidably exists in data collected in many applications. Noise may be present as deviations in attribute values or even as missing values. Low data quality and the presence of noise bring a huge challenge to outlier detection. They can distort the data, blurring the distinction between normal objects and outliers. Moreover, noise and missing data may hide outliers and reduce the effectiveness of outlier detection. An outlier may appear disguised as a noise point, and an outlier detection method may mistakenly identify a noise point as an outlier. Understandability. In some application scenarios, a user may want to not only detect outliers, but also understand why the detected objects are outliers. To meet the understandability requirement, an outlier detection method has to provide some justification of the detection. For example, a statistical model can be used to justify the degree to which an object may be an outlier based on the likelihood that the object was generated by the same mechanism that generated the majority of the data. The smaller the likelihood, the more unlikely the object was generated by the same mechanism, and the more likely the object is an outlier. Parallel approach to clustering. Parallel clustering algorithms. Clustering is to group data objects into classes of similar objects based on their attributes. Each class, called a cluster, consists of objects that are similar between themselves and dissimilar to objects in other classes. The dissimilarity or distance between objects is measured by the given attributes that describe each of the objects. As an unsupervised learning method, clustering is widely used in many applications, such as pattern recognition, image processing, gene expression, on data analysis, market research, and so on. Existing clustering algorithms can be categorized into partitioning, hierarchical, density-based, grid-based, and model-based methods. HKOO, each generating very different clusters for various applications. Parallel K-means, parallel hierarchical clustering, parallel HOP, clustering spatial data, clustering high-dimensional data. Parallel K-means. As a partitioning method, the K-means algorithm, MAX67, takes the input parameter K and partitions a set of n objects into K clusters with high intra-cluster similarity and low inter-cluster similarity. It starts by randomly selecting K objects as the initial cluster centroids. Each object is assigned to its nearest cluster based on the distance between the object and the cluster centroid. It then computes the new centroid or mean for each cluster. This process is repeated until the sum of squared error SSE for all objects converges. The SSE is computed by summing up all the squared distances, one between each object and its nearest cluster centroid. In parallel K-means DMOO, data parallelism is used to divide the workload evenly among all processes. Data objects are statically partitioned into blocks of equal sizes, one for each process. Since the main computation is to compute and compare the distances between each object and the cluster centroids, each process can compute on its own partition of data objects independently if the K cluster centroids are maintained on all processes. The algorithm is summarized in the following steps. Partition the data objects evenly among all processes. Select K objects as the initial cluster centroids. Each process assigns each object in its local partition to the nearest cluster, computes the SSE for all local objects, and sums up local objects belonging to each cluster. All processes exchange and sum up the local SSEs to get the global SSE for all objects and compute the new cluster centroids. Repeat steps 3 to 5 above until there is no change in the global SSE. The algorithm is proposed on distributed memory multiprocessors, but works similarly on shared memory systems as well. Step 3 above is a major computation step where clusters are formed. Objects belonging to one cluster may be distributed over multiple processes. In step 4, each of the new cluster centroid is computed in the same way as the global SSE for all objects, except that the summational result will be further divided by the count of objects in the cluster in order to get the mean. The data objects are partitioned between two processes and the two clusters are identified through 3 iterations. In parallel k-means, the workloads per iteration are fairly well balanced between processes, which result in linear speedups when the number of data objects is large enough. Between iterations, there is a small communication synchronization overhead for all processes to exchange the local SSEs and the local member object summations for each cluster. The algorithm needs a full scan of the data objects in each iteration. For large disk-resident datasets, having more processors could result in superlinear speedups, as each data partition then may be small enough to fit in the main memory, avoiding disk I/O except in the first iteration. K-means clustering. K equals 2 on two processes. One process computes on the objects in gray color and the other is in charge of those in black. Cluster centroids, marked by plus, are maintained on both processes. Circles in solid lines denote the cluster formation in each iteration based on the current cluster centroids. Dashed circles mark the previous cluster formation that is used to compute new cluster centroids. Parallel hierarchical clustering. Hierarchical clustering algorithms are usually applied to bioinformatics procedures such as grouping of genes and proteins with similar structure, reconstruction of evolutionary trees, gene expression analysis, etc. An agglomerative approach is commonly used to recursively merge pairs of closest objects or clusters into new clusters until all objects are merged into one cluster or until a termination condition is satisfied. The distance between two clusters can be determined by single link, average link, complete link, or centroid-based metrics. The single link metric uses the minimum distance between each pair of intercluster objects, average link uses the average distance, and complete link uses the maximum. The centroid-based metric uses the distance between the cluster centroids. The dendrogram on the right shows which clusters are merged at each step. The hierarchical mergence of clusters can be parallelized by assigning clusters to different processes so that each process will be in charge of a disjoint subset of clusters. When two clusters are merged, they are released from the owner processes and the new cluster will be assigned to the least loaded process. The basic parallel algorithm for agglomerative hierarchical clustering takes the following steps. Initially, treat each data object as a cluster and assign clusters among all processes evenly so that each process is responsible for a disjoint subset of clusters. Calculate the distance between each pair of clusters in parallel, maintaining a nearest neighbor for each cluster. All processes synchronously find the closest pair of clusters, agglomerate them into a new cluster, and assign it to the least loaded process. Calculate the distance between the new cluster and each of the remaining old clusters and update the nearest neighbor for each cluster on the responsible process. Repeat steps 3 to 5 above until there is only one cluster remaining or certain termination conditions are satisfied. The algorithm works for both shared and distributed memory multiprocessors, though the latter case requires all processes to exchange data objects in the initialization step of 2. It is crucial to design an appropriate data structure for the parallel computation of the all pair distances between clusters. For steps 2, 3, and 4 above, a two-dimensional array can be used to store distances between any two clusters. It is distributed over all processes such that each one is responsible for those rows corresponding to its assigned clusters. Similarly, the nearest neighbor of each cluster and the associated distance are maintained in a one-dimensional array, with the responsibility divided among processes accordingly. The closest pair of clusters can then be easily determined based on the nearest neighbor distances. Step 3 above is a synchronous phase so that all processes know which two clusters are merged. After two clusters are merged into a new cluster, each process only updates the assigned rows to get the distances from the assigned clusters to the new cluster. Specifically, the distance from cluster I to the new cluster is computed from the distances between cluster I and the two old clusters that are merged. For example, by taking the less value when the single link metric is used. The nearest neighbor information is then recomputed, taking into account the newly computed distances. The assignment of the new cluster requires estimation of the workload on each process. Compute update intercluster distances and nearest neighbors in parallel over two processes. From A to B, clusters A and B are merged into a new cluster AB. In B, only entries in bold font require new computation or updates. Parallel hop, clustering spatial data. HOP, a density-based clustering algorithm proposed in astrophysics, identifies groups of particles in n-body simulations. It first constructs a KD tree by recursively bisecting the particles along the longest axis so that nearby particles reside in the same subdomain. Then it estimates the density of each particle by its n-dense nearest neighbors that can be efficiently found by traverse of the KD tree. Each particle is associated to its densest neighbor within its n-hop nearest neighbors. A particle can hop to the next densest particle and continues hopping until it reaches a particle that is its own densest neighbor. Finally, hop derives clusters from groups that consist of particles associated to the same densest neighbor. Groups are merged if they share a sufficiently dense boundary according to some given density threshold. Particles whose densities are less than the density threshold are excluded from groups. Besides the cosmological n-body problem, HOP may find its application in other fields, such as molecular biology, geology, and astronomy, where large spatial data sets are to be processed with similar clustering or neighbor-finding procedures. To parallelize the HOP clustering process, the key idea is to distribute the data particles across all processes evenly with proper data placement so that the workloads are balanced and communication cost for remote data access is minimized. The following steps explain the parallel hop algorithm in detail, assuming distributed memory multiprocessors. Constructing a distributed KD tree. The particles are initially distributed among all processes in blocks of equal sizes. Starting from the root node of the KD tree, the algorithm first determines the longest axis D and then finds the median value of M of all particles and coordinates in parallel. The whole spatial domain is bisected into two subdomains by M. Particles are exchanged between processes such that the particles whose D coordinates are greater than M go to one subdomain and the rest of the particles to the other one. Therefore, an equal number of particles are maintained in each subdomain after the bisection. This procedure is repeated recursively in every subdomain till the number of subdomains is equal to the number of processes. Then each process continues to build its own local tree within its domain until the desired bucket size, number of particles in each leaf, is reached. Note that inter-process communication is not required in the construction of the local trees. A copy of the whole tree is maintained on every process so that the communication overhead incurred at performing search domain intersection test with the remote local trees at stages 2 and 3 can be reduced. Therefore, at the end of this stage, local trees are broadcasted to all processes. The information contained in a non-leaf tree node includes the aggregated mass, center of mass, number of particles, and domain boundaries. When the KD tree is completed, particles are divided into spatially closed regions of approximately equal number. The advantage of using a KD tree is not only its simplicity, but also the balanced data distribution. Generating density. The density of a particle is estimated by its n-dense nearest neighbors, where n-dense is a user-specified parameter. Since it is possible that some of the n-dense neighbors of a particle are owned by the remote processes, communication is required to access non-local neighbor particles at this stage. One effective approach is, for each particle, to perform an intersection test by traversing the global tree with a given initial search radius r, while keeping track of the non-local intersected buckets. If the total number of particles in all intersected buckets is less than n-dense, the intersection test is reperformed with a larger radius. Once tree walking is completed for all local particles, all the remote buckets containing the potential neighbors are obtained through communication. Note that there is only one communication request to each remote process to gather the intersected buckets. No further communication is necessary when searching for its n-dense nearest neighbors. Since the KD tree displays the value of spatial locality, particle neighbors are most likely located in the same or nearby buckets. According to the experimental results, the communication volume is only 10 to 20% of the total number of particles. However, with highly irregular particle distribution, communication costs may increase. To calculate the density for particle P, the algorithm uses a PQ tree, priority queue, to maintain a sorted list of particles that are currently the n-dense nearest neighbors. The root of the PQ tree contains the neighbor farthest from P. If a new neighbor whose distance to P is shorter than the root replaces the root with the second farthest one and update the PQ tree. Finally, the particles remained in the PQ tree are n-dense nearest neighbors of P. Hopping. This stage first associates each particle to its highest density neighbor among its n-hop nearest neighbors that are already stored in the PQ tree generated at the previous stage. Each particle then hops to the highest density neighbor of its associated neighbor. Hopping to remote particles is performed by first keeping track of all the remote particles and then by making a communication request to the owner processes. This procedure may repeat several times until all the needed non-local particles are already stored locally. Since the hopping is in density increasing order, the convergence is guaranteed. Grouping. Particles linked to the same densest particles are defined as a group. However, some groups should be merged or refined according to the chosen density thresholds. Thus, every process first builds a boundary matrix for the groups constructed from its local particles and then exchanges the boundary matrix among all processes. Particles whose densities are less than a given threshold are excluded from groups, and two groups are merged if their boundary satisfies some given threshold. Intersection test for particle P on process P2 for n-dense equals 7. The neighborhood is a spherical region with a search radius r. The neighborhood search domain of P intersects with the subdomains of P0 and P3. Clustering high-dimensional data. For high-dimensional data, grid-based clustering algorithms are usually used. Click is one of such algorithms. It partitions the n-dimensional data space into non-overlapping rectangular units of uniform size, identifying the dense units among these. Based on a user-specified global density threshold, it iteratively searches dense units in the subspaces from one dimension through k dimension until no more dense units are found. The generation of candidate subspaces is based on the a priori property used in association rule mining. The dense units are then examined to form clusters. The PMA-FIA algorithm improves click by using adaptive grid sizes. The domain of each dimension is partitioned into variable-sized adaptive grid bins that capture the data distribution. Also, variable density thresholds are used, one for each bin. Adaptive dense units are then found in all possible subspaces. A unit is identified as dense if its population is greater than the density thresholds of all the bins that form the unit. Each dense unit of dimension D can be specified by the D dimensions and their corresponding D bin indices. PMAFIA is one of the first algorithms that demonstrate a parallelization of subspace clustering for high-dimensional large-scale datasets. Targeting distributed memory multiprocessors, it makes use of both data and task parallelism. The major steps are listed below. Partition the data objects evenly among all processes. For each dimension, by dividing the domain into fine bins, each process scans the data objects in its local partition and builds a local histogram independently. All processes exchange and sum up the local histograms to get the global one for each dimension. Determine adaptive intervals using the global histogram in each dimension and set the density threshold for each interval. Each process finds candidate dense units of current dimensionality, initially 1, and scans data objects in its local partition to populate the candidate dense units. All processes exchange and sum up the local populations to the global one for each candidate dense unit. Identify dense units and build their data structures. Increase the dimensionality and repeat steps 5 to 8 until no more dense units are found. Generate clusters from identified dense units. Identification of dense units in two-dimensional grids. A uses a uniform grid size, while B uses adaptive grid sizes by merging fine bins into adaptive grid bins in each dimension. Histograms are built for all dimensions. The algorithm spends most of its time in making repeated passes over the data objects and finding out the dense units among the candidate dense units formed from one-dimensional to k-dimensional subspaces until no more dense units are found. Building the histograms in step 2 and populating the candidate dense units in step 5 are performed by data parallelism, such that each process scans only a partition of data objects to compute the local histograms and local populations independently. After each of the independent steps, the local values are collected from all processes and add up to the global values as in steps 3 and 6 respectively. In step 4, all processes perform the same adaptive grid computation from the global histograms they gathered. The adaptive grid bins in each dimension are then generated, each considered to be a candidate dense unit of dimension 1. Candidate dense units from subspaces of higher dimensions need to be generated in step 5. Similar to the candidate subspace generation procedure in CLIC, PMAFIA generates candidate dense units in any dimension k by combining dense units of dimension k1 such that they share any k2 dimensions. Since each pair of the dense units needs to be checked for possible intersection into a candidate dense unit, the amount of work is known and the task can be easily subdivided among all processes such that each one intersects an equal number of pairs. Task parallelism is also used in step 7 to identify dense units from the populated candidates such that each process scans an equal number of candidates' dense units. PMAFIA is designed for disk-resident data sets and scans the data as many times as the maximum dimension of the dense units. By data parallelism, each partition of data is stored in the local disk once it is retrieved from the remote shared disk by a process. That way, subsequent data accesses can see a much larger I/O bandwidth. It uses fine bins to build the histogram in each dimension, which results in large sizes of histograms and could add to the communication cost for all processes to exchange local histograms. Compared to the major time spent in populating the candidate dense units, this communication overhead can be negligible. Also, by using adaptive grids that automatically capture the data distribution, the number of candidate dense units is minimized, so is the communication cost in the exchange of the local populations among all processes. Partition-based clustering. The simplest and most fundamental version of cluster analysis is partitioning. which organizes the objects of a set into several exclusive groups or clusters. To keep the problem specification concise, we can assume that the number of clusters is given as background knowledge. This parameter is a starting point for partitioning methods. Formally, given a dataset D of n objects and k the number of clusters to form, a partitioning algorithm organizes the objects into k partitions. K is less or equal to n, where each partition represents a cluster. The clusters are formed to optimize an objective partitioning criterion, such as a dissimilarity function based on distance, so that the objects within a cluster are similar to one another and dissimilar to objects in other clusters in terms of the dataset attributes. K-means, a centroid-based technique. Suppose a dataset D contains n objects in Euclidean space. Partitioning methods distribute the objects in D into k clusters C1 ... Ck. That is, Ci is a proper subset of D, and Ci intersection Cj equals null for I, j lying between 1 and k. An objective function is used to assess the partitioning quality so that objects within a cluster are similar to one another but dissimilar to objects in other clusters. This is, the objective function aims for high intra-cluster similarity and low inter-cluster similarity. A centroid-based partitioning technique uses the centroid of a cluster Ci to represent that cluster. Conceptually, the centroid of a cluster is its center point. The centroid can be defined in various ways, such as by the mean or medoid of the objects, or points assigned to the cluster. The difference between an object P belonging to Ci and Ci, the representative of the cluster, is measured by distance of P, Ci, where distance of x, y is the Euclidean distance between 2 points x and y. The quality of cluster Ci can be measured by within cluster variation, which is the sum of squared error between all objects in Ci and the centroid Ci, defined as E equals double summation I equals 1 to k, P belongs to Ci, distance of P, Ci whole squared, where E is the sum of the squared error for all objects in the dataset, P is a point in space representing a given object, and Ci is the centroid of cluster Ci. Both Pi and C are multidimensional. In other words, for each object in each cluster, the distance from the object to its cluster center is squared, and the distances are summed. This objective function tries to make the resulting k clusters as compact and as separate as possible. How does a k-means algorithm work? The k-means algorithm defines the centroid of a cluster as the mean value of the points within the cluster. It proceeds as follows. First, it randomly selects k of the objects in D, each of which initially represents a cluster mean or center. For each of the remaining objects, an object is assigned to the cluster to which it is the most similar based on the Euclidean distance between the object and the cluster mean. The k-means algorithm then iteratively improves the within cluster variation. For each cluster, it computes the new mean using the objects assigned to the cluster in the previous iteration. All the objects are then reassigned using the updated means as the new cluster centers. The iterations continue until the assignment is stable, that is, the clusters formed in the current round are the same as those formed in the previous round. Algorithm k-means. The k-means algorithm for partitioning, where each cluster's center is represented by the mean value of the objects in the cluster. Input k, the number of clusters, D, a dataset containing n objects. Output, a set of k clusters. Method, arbitrarily choose k objects from D as the initial cluster centers. Repeat. Reassign each object to the cluster to which the object is most similar based on the mean value of the objects in the cluster. Update the cluster means, that is, calculate the mean value of the objects for each cluster until no change. The process of iteratively reassigning objects to clusters to improve the partitioning is referred to as iterative relocation. To obtain good results, the k-means algorithm is run multiple times with different initial cluster centers. The time complexity of the k-means algorithm is big O of nkt, where n is the total number of objects, k is the number of clusters, and t is the number of iterations. Normally, k is much less than n, and t is much less than n. Therefore, the method is relatively scalable and efficient in processing large datasets. There are several variants of the k-means method. These can differ in the selection of the initial k-means, the calculation of dissimilarity, and the strategies for calculating cluster means. The k-means method can be applied only when the mean of a set of objects is defined. The k-modes method is a variant of k-means, which extends the k-means paradigm to cluster nominal data by replacing the means of clusters with modes. The k-means and the k-modes method can be integrated to a cluster data with mixed numeric and nominal values. K-medoids, a representative object-based technique. The k-means algorithm is sensitive to outliers because such objects are far away from the majority of the data, and thus, when assigned to a cluster, they can dramatically distort the mean value of the cluster. This inadvertently affects the assignment of other objects to clusters. This effect is particularly exacerbated due to the use of squared error function. How can we modify the k-means algorithm to diminish such sensitivity to outliers? Instead of taking the mean value of the objects in a cluster as a reference point, we can pick actual objects to represent the clusters, using one representative object per cluster. Each remaining object is assigned to the cluster, of which the representative object is the most similar. The partitioning method is then performed based on the principle of minimizing the sum of the dissimilarities between each object P and its corresponding representative object. That is, an absolute error criterion is used, defined as E equals summation of I equals 1 to k, summation of P belongs to Ci, distance of P, Oi, where E is the sum of the absolute error for all objects P in the dataset and Oi is the representative object of Ci. This is the basis for the k-medoids method, which groups n objects into k clusters by minimizing the absolute error. When k equals 1, we can find the exact median in big O n squared time. However, when k is a general positive number, the k-medoid problem is NP-hard. The partitioning around medoids PAM algorithm is a popular realization of k-medoids clustering. Like the k-means algorithm, the initial representative objects, called seeds, are chosen arbitrarily. We consider whether replacing a representative object by a non-representative object would improve the clustering quality. The iterative process of replacing representative objects by other objects continues until the quality of the resulting clustering cannot be improved by any replacement. This quality is measured by a cost function of the average dissimilarity between an object and the representative object of its cluster. Which method is more robust, k-means or k-medoids? The k-medoids method is more robust than k-means in the presence of noise and outliers because a medoid is less influenced by outliers or other extreme values than a mean. However, the complexity of each iteration in the k-medoids algorithm is big O into k of n minus k whole squared. For large values of n and k, such computation becomes very costly and much more costly than the k-means method. Both methods require the user to specify k, the number of clusters. How can we scale up the k-medoids method? A typical k-medoids partitioning algorithm, like PAM, works effectively for small datasets but does not scale well for large datasets. To deal with larger datasets, a sampling-based method called CLARA, clustering large applications, can be used. CLARA uses a random sample of the dataset. The PAM algorithm is then applied to compute the best medoids from the sample. Ideally, the sample should closely represent the original dataset. CLARA builds clusterings from multiple random samples and returns the best clustering as the output. The effectiveness of CLARA depends on the sample size. PAM searches for the best k-medoids among a given data set, whereas Clara searches for the best k-medoids among the selected sample of the data set. Clara cannot find a good clustering if any of the best sampled medoids is far from the best k-medoids. If an object is one of the best k-medoids but is not selected during sampling, Clara will never find the best clustering. How might we improve the quality and scalability of Clara? When searching for better medoids, PAM examines every object in the dataset against every current medoid, whereas Clara confines the candidate medoids to only a random sample of the dataset. A randomized algorithm called Clarence, clustering large applications based upon randomized search, presents a trade-off between the cost and the effectiveness of using samples to obtain clustering. First, it randomly selects k objects in the dataset as the current medoids. It then randomly selects a current medoid, x, and an object y that is not one of the current medoids. Can replacing x by y improve the absolute error criterion? If yes, the replacement is made. Clarence conducts such a randomized search L times. The set of current medoids after the L steps is considered a local optimum. Clarence repeats this randomized process m times and returns the best local optimal as the final result. Algorithm K-medoids. PAM, a K-medoids algorithm for partitioning based on medoid or central objects. Input K, the number of clusters. D, a dataset obtaining n objects. Output, a set of k clusters. Method is as shown on the screen. Types of data in cluster analysis. Data structures. Data matrix. Two modes. The classic data input is shown in the matrix below. Dissimilarity or distance matrix. One mode. The desired data input to some clustering algorithms. Measuring similarity in clustering. Dissimilarity or similarity metric. The dissimilarity D of I, j between two objects I and j is expressed in terms of a distance function, which is typically a metric. D of I, j is greater or equal to 0, non-negativity. D of I, j is 0, isolation. D of I, j equals D of j, I, symmetry. D of I, j is less or equal to D of I, h plus D of h, j, triangular inequality. The definitions of distance functions are usually different for interval-scaled, Boolean, categorical, ordinal, and ratio-scaled variables. Weights may be associated with different variables based on applications and data semantics. Types of data in cluster analysis. Interval-scaled variables, for example, salary, height. Binary variables, for example, gender, male or female, has cancer, true or false. Nominal categorical variables, for example, religion, Christian, Muslim, Buddhist, Hindu, etc. Ordinal variables, for example, military rank, soldier, sergeant, lieutenant, captain, etc. Ratio-scaled variables, for example, population growth, 1, 10, 100, 1000, and so on. Variables of mixed types, for example, multiple attributes with various types. Similarity and dissimilarity between objects. Distance metrics are normally used to measure the similarity or dissimilarity between two data objects. The most popular conform to Minkowski's distance, which is represented on the screen, where I equals xi1, xi2 up to xin and j equals xj1, xj2 going up to xjn are two n-dimensional data objects and p is a positive integer. If p equals 1, L1 is a Manhattan or city block distance shown on the screen. If p equals 2, L2 is the Euclidean distance shown on the screen. Binary variables. A binary variable has two states, 0 absent, 1 present. A contingency table for binary data may be constructed as shown. Simple matching coefficient distance, invariant if the binary variable is symmetric. D I of j equals b plus c over a plus b plus c plus d. Jacquard coefficient distance, non-invariant if the binary variable is asymmetric. D of I comma j equals b plus c over a plus b plus c. Another approach is to define the similarity of two objects and not their distance. In that case, we have the following. Simple matching coefficient similarity. S of ij equals a plus d over a plus b plus c plus d. Jacquard coefficient similarity. S of I comma j equals a over a plus b plus c. Note that S of I comma j equals 1 minus d of I comma j. Variables of mixed types. A database may contain all the 6 types of variables: symmetric binary, asymmetric binary, nominal, ordinal, interval, and ratio scale. One may use a weighted formula to combine their effects as shown on screen. Conclusion. In this chapter, we have covered the following in detail. Types of data in cluster analysis, partition-based clustering, hierarchical clustering, density-based clustering, grid-based clustering, model-based clustering, discussion on scalability of clustering algorithm, outlier analysis, parallel approaches to clustering.